Let's talk about mass and the center of mass really briefly. This is an application of what we've learned so far in calculus. Recall that the center of mass of a system is the point. If all the mass of the system were concentrated there, the total moment is the same as the original. In the discrete case of masses, mi at points xi, yi, the total moment or moment of mass about the y-axis, big My, is equal to the sum of the little mi times the xi, which is that distance from the y-axis. And the moment about the x-axis, mx, is just the sum of the mi, yi. Pretty simple, right? In the discrete case. So the center of mass has the coordinates x bar, y bar, where the sum of the mi times x bar is equal to the sum of mi xi, and similarly for the y case. Thus, we can just calculate x bar and y bar by my over total mass, and similarly for y bar. We can easily generalize this to R3 as well, with a z bar with mxy over the total mass, where mxy is just the sum of mi zi and is the total moment around the xy plane. All of this should be very familiar to a lot of what we've done previously. It's just a very simple generalization in the discrete case. So what is this in terms of calculus? Let's suppose we had this type of object in R2 with a certain density function. Then the total mass of D is just going to be the double integral over the domain of the density with our dA. Using the discrete case as a guide, we would also find that my is equal to x times the density, the integral of this dA, and similarly for mx. So the center of mass has the following coordinates. M bar, y bar is equal to the double integral x with our density dA over the double integral, the density dA, and the same for the y coordinates. Pretty simple, and it's just about using what we know on how to do double integrals and being able to calculate these. Pretty simple. And the equations for solid regions in R3 are just kind of the exact same thing, just extend it and generalize it yourself. But mass and center of mass should be no big deal.